everyone. Today, my colleague Manoj and I are going to discuss about an algorithm for distributed computation of spanning tree in an extended LAN. It is a protocol and a technique in which bridge is in an Hello everyone. Today, my colleague Manoj and I are going to discuss about an algorithm for distributed computation of spanning tree in an extended LAN. It is a protocol and a technique in which bridges in an extended LAN of an arbitrary topology compute an acyclic spanning subset of the network in a distributed way. Now, let me give you a brief introduction about this algorithm. Since geographically, traffic-wise, and in terms of station count, local area networks are constrained. For these reasons, a single local area network will frequently fail to satisfy organizations' requirements. This algorithm provides a technique that is transparent to station and hence allows the station to join an extended LAN without any modifications. A bridge linked to two or more connections will listen to all the packets transmitted on each link and pass the packets received on one of its links to other in this method. A bridge also learns a relative location of the station, so the traffic for each station is not sent onto the connection needlessly. The topology is assumed to be tree, that is, a loop-free, which is called the spanning tree. However, needing a loop-free topology means that the event of bridge or LAN failure, there is no backup channels. Furthermore, because of the technology allows for a rapid network expansion, it may be impossible to prevent someone from adding a bridge or forming a loop. Due to congestions produced by infinite cycling packets, a loop in the topology might cause a substantial performance deterioration over the whole extended network. It's inconvenient to have the network that can be shut down so quickly just by inserting a cable into the incorrect location, right? So, as a result, they develop an algorithm that has a method that permits the extended network to have any topology. The bridges perform the method which compute a subset of the topology that links all the LANs while being a loop-free spanning tree. It's a self-configuring algorithm. The only prior information required in a bridge is its own unique ID that is called hack address, that is HAC address, which we assume to be obtained in some way, that is by using a hardware ROM carrying the value. In this slide, we'll be discussing the common terminologies. First, coming to station. Station is an extended LAN node that does not forward packets. It's only connected to the extended LAN in order to communicate with the other stations. It's not a part of the spanning tree algorithm. Next, coming to the bridge. A bridge is a node that is linked between two or more LANs in order to forward packets between the LANs. And a link is a connection between a bridge and a single LAN. Coming to an extended LAN is a group of LANs linked together via bridges. And the root is the bridge chosen to be the root of the newly created spanning tree. There is only one root in this network, which is chosen dynamically. Finally, designated bridges. Designated bridges is the bridge on the LAN closest to the root, with a tiebreaker to ensure uniqueness. As a result, there is only one designated bridge per LAN in the network, which is chosen dynamically too.
Now let's discuss about the goals we are trying to achieve with this algorithm. The first one is allow interconnection of LANs compatibly with LAN standards so that stations need not know whether they are attached to a single LAN or to a network of LANs. Allow redundant bridges and LANs in an extended LAN, for instance, so that connectivity can be preserved after bridge or LAN failures. Be self-configuring so that each bridge need only know its own ID and a well-known generic group address. Many requirements of the bridge should not grow with the number of LANs or bridges so that a network can be misconfigured. The communications bandwidth consumed by the algorithm on any particular LAN should be a constant, regardless of the total number of bridges or LANs in the net. The algorithm should stabilize as quickly as possible to deterministic spanning tree in any network. Assuming no lost messages, it should stabilize in some small multiple of the round delay across the network. The algorithm should allow bridges to keep cache of station membership to cut down on traffic. No permanent loops should ever form. The algorithm should be self-stabilizing once any malfunctioning equipment is repaired or disconnected. The algorithm should break loops even if some of the bridges in the loop do not implement the algorithm.
The modifications required to allow extension designations are discussed in this section. Now, let's look at the algorithm in detail. First, we elect the root and designated bridges. To do so, the root is the network bridge with the smallest ID. When a bridge receives a hello message, it compares its ID to the root in the hello message to the best known root available at that time. If the root in the hello message has a lower ID than the presently known root, the existing root's information is destroyed and newly found root's information is rewritten. On a LAN, the designated bridge is the bridge with the shortest path to the root. In the case of tie, the designated bridge on the LAN is the bridge that has the smallest ID. And other bridges calculate their distance from the root as one or more minimum distance obtained from the designated bridge on any associated LAN through a hello message. Because it is the only bridge that is zero from the root is the designated bridge on each of its LAN. Any other bridge is separated from the root by distance k. Receiving a hello message from the designated bridge, one of its connection carrying hops or gives k minus 1 gave its distance k. As a result, bridges that aren't the root can't be designated bridges of all their LANs. One of the LANs must have the bridge that is closer to the root. Next, the transmission of hello messages. The root sends out a hello message to each of its link on a regular basis using the term hello time. Other bridges will only broadcast a hello on a connection if there are LAN designated bridges. Because each LAN has precisely one designated bridge, each LAN's bridge will send a hello message on a regular basis. The age of this information, included in the hello packet, is indicated by the age of hello packet. A designated bridge will typically send a hello only if it receives hello on the link of the root from the younger age. A designated bridge, on the other hand, will send a hello on a specific connection if it receives a hello from a different bridge on the LAN that isn't the designated bridge. Then the information is deleted if the age file exceeds a certain limit. As a result of the failure of the root or a designated bridge, the other bridges are prompted to calculate a new route or a path to the root. Next, link states and the databases. Each bridge maintains per link database for each of its link, which includes information such as state of the link, information from the most recent hello message from the designated bridge on the LAN, whether a node that should send a hello message on the link, and a timer which is activated in the pre-forwarding stage and the pre-backup stage, and whose expiration will be moved to the link or pre-forwarding to forwarding stage or pre-backup to backup stage. Next, we have state transactions. The information in the link database is replaced whenever a hello message is received that overrides with what is recorded in the link database. The timer pulse causes the root to send a fresh hello message each bridge to update age of the information in the link database and links to the transition from pre-forwarding or pre-backup states if there is a delay has transpired. Let's suppose bridge B recomputes its own distance from the root and examines each connection to the B should be taken over as a designated bridge when information in the link database changes. That means it's either reception of a different or a superior of a hello message or expiration of a stored hello information. If the existing root's information has expired, B will strive to become the new root and the designated bridge on each of its LAN. If B is not the root, it chooses a single connection that is closest to it. If there are many links that are equally near to the root, B picks one random root. B tries to make its link status forwarding by doing the following state. The status of the connection is changed to forwarding instantly if it is in forwarding or pre-backup state. if nothing is done, if it is in pre-forwarding stage. The status of the connection is changed to pre-forwarding stage and the timer is set to pre-forwarding delay if it is in backup. Similarly, B tries to make the condition of each connection for B in designated bridge forwarding. B attempts to make a state backup for each of its other connections, that is, links other than one nearest to the root or for the B in a designated bridge as follows. If the connection is in backup or pre-forwarding mode, it is converted to backup mode instantly. Nothing will be done if the connection is in pre-backup state. The state of the link is changed to pre-backup as the timer is set to pre-backup delay if the link is in forwarding state. You can see that in the given diagram. After the state transitions, we will be handling the data traffic. Assuming that all the connections are now in the forwarding state, the following is how the forwarding database is used. The source field of the packet is used to build the forwarding database. The destination field determines how the traffic is sent. If a packet with a destination D and the source S is received on the link L, an entry is made in the forwarding database indicating that S is located in the direction of link L. However, links can be in the state other than forwarding state. Then, these rules are to be followed. One, that is, when a traffic is received from a link that is in backup state, it is ignored. Next, the data traffic from the other states is inspected for the source addresses in order to update the forwarding database. The other states are forwarding, pre-forwarding, and pre-backup states. During the forwarding and pre-backup stages, data traffic is forwarded to and from the connections. This is how the data traffic is handled. Next, let's look into the interaction between simple bridges. Basically, simple bridges are those that does not participate in this algorithm but transparently sends hello message all over. As a result, LAN connected by a simple bridge will be appear to be a single LAN with when using this approach. We have timer values that have timer settings such as max delay, max lost packets, and max prop time. Max delay is the maximum one-way delay across the extended LAN. Max lost messages are the maximum number of consecutive messages within an acceptable probability that are lost. And the max prop time is the maximum delay plus hello time into max lost messages. Then we have maximum age. Max age is a parameter that should be equal to or more than the max prop time. And moving on to pre-backup delay, it is a bridge that retains a link in the state pre-backup for the time pre-backup delay before converting it from forwarding to backup to prevent the transitory partitions. Next, we have pre-forwarding delay. In this delay, a bridge retains a connection in a state where pre-forwarding for a time pre-forward delay before switching it from the state backup to state forwarding to avoid the transition to. Then we have to set the parameters. The parameters that are to be set are hello time and the max age. Hello time and the max age are the network management settable parameters that allows adjustment of a specific configuration that is other than the timers and the derived max age. Hello time can vary from bridge to bridge as long as root's hello time does not break the inequality that the max age must be more than or equal to max prop time. As a result, hello time may be adjustable individually on each bridge with a suitable default ensuring that the performance is satisfactory even if the parameter is not set. Finally, the network must however agree on max age, that is, max age from which the other parameters are calculated is supplied to hello messages to guarantee the consistency and the number of passed by the routes is utilized. Now, my friend Manoj will be explaining the analysis of this algorithm.
Coming to the analysis part, first we have exactly one route in the net. Let's imagine, suppose if we have two routes A and B, with A having the numerically smaller ID than B. If there is a physical connectivity between A and B, there will be some LAN with a path to both A and B. On that LAN, as soon as a bridge issues a hello message with information about A, the other bridges on the LAN will override the information about B. This will propagate eventually to B, which will stop attempting to be a route. And the second one is exactly one designated bridge per LAN. Each bridge has a unique ID. Of all the set of bridges on a LAN that have the smallest hop count from the route, only one of them can have the smallest ID. Thus, there is a unique destination bridge per LAN. A bridge will attempt to become destination bridge on a LAN unless a different bridge which has a better hello message transmits. And the third one is all LANs are included in the formed graph. If there is a physical connectivity between a LAN and the bridge, that is route, then use of the route will have to spread that LAN and the designated bridge will choose because of its path to the route. A bridge which is designated bridge on a LAN will be in the formed graph and will include the LAN in the formed graph as well. Since every LAN has a designated bridge, every LAN is included in the form graph as well. Amount of memory. The amount of memory required for finding an acyclic spanning subset of the topology is the amount needed for the linked database. To keep the IDs of the route and the designated bridge requires the fixed value of 48 bits. To keep the distance from the route in practice requires a fixed value of 16 bits or even 8 bits would suffice. The other pieces of information are fixed length. Bridge B must keep this information for each link attached to B, not each link in the network. And the next one is communications bandwidth. Maintenance of the algorithm when topology has not recently changed requires 1 hello per hello time to be transmitted on each LAN by that LAN's designated bridge. Thus, regardless of the total size of the network, only one control message will be sent each hello time on each LAN unless the topology changes. But if there is a topology change, a few extra hello messages might be transmitted, for instance, by a bridge that has just come up. Additionally, the designated bridge issues a hello in response to more quickly synchronized bridges that have just come up. However, there is no need to do this more frequently than hello time. So a hold down is instituted to prevent a bridge from transmitting more than one hello per hello time. So the maximum amount of control traffic on a LAN even during the topology changes is limited. The formed graph is a tree. The properties of a tree are it has a unique root. Each node other than the root has a unique predecessor closer to the root. The ancestor node of a bridge is the LAN in the direction of the root. The ancestor node of a LAN is the designated bridge. Thus, all nodes have a unique ancestor. Likewise, there is a unique root, which is the bridge with the lowest ID. And the last one is one-way connectivity. Connectivity between bridges can be one-way if one transmitter is broken or the other's receiver is broken. One-way connectivity might be a common hardware failure mode, and it is desirable that the algorithm prevents loops in the face of one-way links from causing loops. A designated bridge will detect a problem if another bridge on the same LAN persists in sending hello messages because that would indicate that the other bridge is not receiving the designated bridge's message. If other node disagrees about the identity of the root, there is no loop. If the other node agrees about the root, there is a loop. And finally, to conclude this presentation, the algorithm presented here maintains a spanning acyclic subset of a general mesh topology. It requires a very small bounded amount of memory per bridge, independent of the total number of LANs or the number of bridges in the network. The computed topology is deterministic. So bridges implementing this algorithm can coexist with simpler bridges that do not implement this algorithm. And loops will still be broken provided that no loop exists composed solely on bridges that do not implement the algorithm. Thank you.